Hi everyone. Hope everyone's doing okay. Can you guys hear me okay? I'm having a little bit of audio trouble. A little fuzzy, but hard to hear. Okay. Now, there we go.
Okay. Maybe now, maybe it's a little bit better now. Yeah. Okay. Yeah, it was using my webcam speaker, which is not the best. Okay. Well, let us begin. Welcome to chapter 4. Now, just a quick reminder, I haven't checked who has done the quiz or not, but first quiz will be due today by 10 p.m. So it takes about an hour, so give yourself some time, knock it out. And then we roughly, just another reminder, roughly every week we have a quiz. So, okay. I've been asked a few questions about sig figs, and I did send an announcement. You may, if you haven't had time to read it, read the announcement, kind of describe sig figs. But the bottom line is this: whenever you present any data, answer a question, do a calculation, not only now, but later down the road in other chapters, always present it with the correct number, significant figures. And again, you can't be more accurate than the least accurate measurement that you're given. Okay. Okay. So if you have any questions, shoot me an email about that, sig figs, but we'll be using sig figs throughout the weeks. All right. Chapter 4. We're going to talk about the atoms and kind of give you some background as to how we came about this model of the atom. Currently, the model is straightforward. We got a nucleus, which consists of a proton and a neutron, and then orbiting around the nucleus are electrons. And so we're going to talk about how this came about. Okay, so Dalton, scientist, lived back in the 1800s. He proposed a theory that an element was made up of tiny indestructible particles called atoms. Okay, now the concept of atoms is not new. The Greeks, in fact, the term atoms comes from the Greeks' thought about how matter was put together. So it's not a new concept, but he kind of refreshed it a little bit. And he thought they were indestructible. Well, that's not quite true, because in modern science now we find out that these particles, the protons, the neutrons, the electrons, are made up of even smaller particles, which we're not going to talk about in this class here. But in fact, it's thought that there is a particle that, in fact, they're searching for right now, trying to find it, that makes up the protons and the electrons. And so very, very, very complicated theory. Okay, so he had a second theory, a second part of this theory, that all atoms of an element are identical and have the same properties. Okay, that sounded good for a while, but that's not quite true. Yes, all atoms of an element are identical, but they may not have the same properties. We talked briefly about carbon, how we have diamonds are made up of nothing but carbon, but we also can make graphite, solid graphite, which is made up of carbon also. And so there's different properties, and it's all dependent on how the elements are put together relative to each other. His other part of this theory said that atoms of different elements combine to form compounds, which is true. When we get two different elements, in this example here, combine to make what we call a compound. So a compound, by definition, is a chunk of matter made up of two or more different atoms. Another part of this theory, which we found to be continues to be true, is that when compounds are formed, they come together with atoms in whole numbers, in whole ratios. For example, water. Water has 2 hydrogens and 1 oxygen in its compound. Okay, they don't come together with, you know, half an atom of hydrogen or 3/4 an atom, and it's one whole. So all of our compounds will always have ratios, even numbers, okay, even whole numbers. Atoms can come together to form different compounds. Here's 2 examples right here where we have CO, capital O, carbon monoxide, the symbol on the model on the left there. The red color sphere represents a big carbon, and then the gray one can represent the oxygen. But carbon monoxide, which we all know is a poisonous gas, okay? But we can also add more oxygen to that process and create carbon dioxide. Okay, so the model on the right represents carbon in the center and then bonded to 2 oxygens. Totally different chemicals, totally different properties, but they come together with even numbers. 1 carbon, 1 oxygen for carbon monoxide, 1 whole atom of carbon, 2 whole atoms of oxygen for carbon dioxide. Now, so here we got the theory going on. A lot of this was coming on in the 1800s, and then we start getting into the early 1900s where the model gets refined a little bit. So one scientist by the name of J.J. Thomson, he's credited to the discovery of the electron way back in 1897. And the way he did that is going to be seen by this particular video that I'm going to show next. Now, if you don't hear the sound, let me know, because maybe I did not set it up properly. But let's take a look at it very quickly.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the 2 metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light. A tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the 2 metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light.
Okay.
When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field.
Uh-oh.
A cathode ray tube is the forerunner of...
Sorry about that. Something went crazy here. Let me move it up a little bit.
Strikes the specially coated surface.
Let me make a quick note here very quickly. So we got these particles that are being generated back here by where you see the cathode and the anode. This is really the precursor of the old-fashioned television that we used to have. On the surface here on the screen, where you can see my mouse moving, hopefully, where it's kind of green, these particles hit that fluorescent screen. Okay, now those particles come in there and it hit the fluorescent screen with a lot of energy, and they transfer that energy onto the material of the screen. They get excited, and nature being nature, we'll talk about that. Any molecule, when it gets excited, will not stay up in the excited state very long, but will drop back down to the ground state, to where the unexcited state. Well, conservation energy tells us that whatever energy you absorb, you have to give it up the same amount of energy. In this case, that fluorescent material, that light, what you see is the energy that it absorbed. Okay, so
cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing.
This is how we realize why it was determined that the electrons have a negative charge, because they put a potential, a current, and on the excuse me, they put a current here given by the blue and the red plates here, and what caused that beam to shift, and it twisted and it moved, and so instead of going straight through, it was affected by that electrical charge that was applied to that screen.
Positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied...
Not to worry about this equation. The thing to take away from this is that that ratio is a ratio of the charge over the mass. And so if you can determine one of those variables, guess what? You can calculate the other. And so later on down the road, scientists were able to calculate the charge and determine the actual mass of the electron. So
electric field. Theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Okay, so J.J. Thomson then proposed a theory which now kind of changed the theory that was going on. It said, they call it the plum pudding theory, in which the atom consisted of some species that was positive charge, and is denoted by that diagram there, and that the electrons were kind of displaced all over the place. He didn't really define it as to where these electrons were specifically. So that model went along for a while until another scientist by the name of Ernest Rutherford was able to, he's credited with discovering the nucleus, or the proton, nucleus/proton. And he did a similar experiment, but what he did was taking particles, and not to worry about the type of particles, but they're called alpha particles, and he hit these particles on a gold foil, okay? He used a similar system that J.J. Thomson did with the fluorescent material, and he was expecting, based on the plumbing model, that there should not be no deflection. But he was surprised. These particles are being deflected. Okay, and one can think of it as if you shot a bullet into a Kleenex and that bullet came right back to you, just to put it in relative terms. So it was quite shocking. So here's the next video explaining his experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they...
You can see here where the fluorescent materials, it gets exciting. You see the color here. As he shot the particles through the gold foil, he was expecting all the particles just to go through. But a lot of them were being deflected, going different angles, left and different, and also go all the way back to the sensor. So that was pretty exciting because that stated that there must be something that's pretty heavy that these particles are hitting, causing it to be deflected. Sort of like shooting pool. I don't know if you ever shot pool or billiards, and you want to shoot the cue ball and you want to get a ball into a pocket, you got to give it the right angle and so forth. So instead of going straight forward, you can make the cue ball go off to the left, right, or whatever angle.
It collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay. And so we have now the model on the far left, which was Thomson's model, had the plum pudding model. Didn't quite fit after Rutherford presented his data, because you can see on the diagram on the right that the particles are being ricocheted off, which meant that they were hitting something pretty heavy, pretty high density in the center of the atom. So he proposed that there is a nucleus, and in that nucleus we find out that became mostly the proton. Eventually, we've determined by another scientist the neutron. So the electron was first determined. Okay, then 1917, Rutherford is credited discovering the proton, or the nucleus, if you will. And then it was not until like the 1930s, another scientist called Sadway is credited with discovering the neutron. Okay. We find out through calculations that the atom is mostly empty space, with the electrons roaming around the nucleus. Now, at this point, we just have the nucleus roaming around the electrons orbiting the nucleus. We will find later on that these electrons are in specific energy levels, very specific. Okay. All right, so each atom has a very small dense nucleus, and in the center of the nucleus we have the protons and the neutrons with the orbits, the electrons orbiting around the nucleus. Now, to put this in perspective with respect to size and how much space is in here, if the nucleus was the size of, say, a small marble, then the atom would be the size of the football stadium, Cardinals football stadium. So it's a lot of empty space there. And something to think about. The electrons are negative charge, and they're all around us. So when you hold on to something, you're not really touching it, because electrons repel each other. And so the electrons on your fingers are repelling the electrons on the object that you are holding. And yes, your hand overpowers that force, but they're so separated, and you're not really touching or holding on to any material. It's just the electrons are separating. The materials are separated or pulled apart, repel because of the electrons. So we have three subatomic particles, okay? We have the electron, we have the proton, and we have the neutron. They each have a symbol. The electron has a lowercase e with a superscript negative, because the electron has a negative charge. The proton has a positive charge, and it's denoted by the symbol of lowercase p with a superscript positive. And the neutron, no charge. That its symbol is denoted by the letter N. Now, with respect to location and where it's at, electrons are outside the nucleus, and in the nucleus are the protons and the neutrons. The charge column, -1 for electrons, +1 for protons, and 0 for the neutron, because no charge. Now, we introduce a concept here called atomic mass unit, AMU. Okay, these subatomic particles are very, very small, so we give them a relative weight relative to each other. The protons and the neutrons have been given a relative weight of 1, and the electrons are so tiny that their relative weight is roughly 1 over 1836. Pretty small. To give you an idea how small these electrons are, if you have something that weighed 2,000 pounds, the electron will be about 1/10 of a pound. Extremely tiny with respect to mass. However, the electrons are very powerful. All chemistry, everything that we know, all the properties, all the chemical reactions are brought to you, occur because of the electrons. You lose one electron, you totally change the properties completely, 100%. Okay, so for as far as the atomic mass unit, the electron is, because it's so small, it's relatively 0, approximately 0. So atomic mass units for electron is 0, for the proton is 1, and the neutron is 1. Okay, so let's go back to the elements. Okay, we have what's called atomic notation. SY here represents the element symbol. Okay, now if you haven't done so yet, make sure you download the periodic table. Okay, so here you got the periodic table that we use quite a bit. All right, here are all the elements, 118 elements. They have their symbol. And that number on top of each symbol, for example, carbon, that's the atomic number. We're going to talk a lot about that. We're going to refer to the atomic periodic table quite a bit, because you're going to be able to get a lot of information about the particular element that we're going to talk about just by finding it on the periodic table. All right, so SY represents the symbol. Now, superscript left, where the letter A is, we call that the mass number. Okay, the mass number, which is a whole number. Okay, now when we talk about the mass weight or the atomic weight, that number is a decimal number, but the mass number is a whole number. The atomic number, superscript Z, subscript Z on the left, is the atomic number. That number tells you how many protons and how many electrons. Okay, the mass number is the sum of the protons and the neutrons, and is always a whole number. So if we go back to the periodic table, okay, we can get any element here, and let's just, for argument's sake, aluminum, number 13. Okay, aluminum has 13 protons and 13 neutrons. Okay, carbon, number 6, 6 protons, 6 electrons. Okay, oxygen, number 8, 8 protons, 8 electrons. Okay, now the mass number, again, which is a whole number, is the sum of the protons and the neutrons. Therefore, if we know how many protons and we know the mass number, we can calculate how many neutrons that element has. let's, oh, wrong direction. So every atom of an element has the same number of protons, okay, which is also the same number of electrons. The protons, put this in long-term memory. The protons have a positive charge and the electrons have a negative charge. So the net charge of all the elements is 0, okay? So carbon has 6 protons, which are positive, 6 electrons, which are negative. The overall charge for the element is 0, okay? Later down the road, we're going to be seeing the elements either losing electrons or gaining electrons, which changes the net charge, okay, to either be positive or negative and producing what we call ions. Okay, so the number of protons defines an element. Now, this is also important. We can lose neutrons, we can lose electrons all day, but the element, as long as we don't lose the proton, the element remains the same. Okay, so again, this is very crucial. If we take a look at carbon, it has 6 protons, 6 electrons. I could lose those 6 electrons, but I still have carbon. I can gain electrons, but I still have carbon. The moment carbon number 6 gains a proton, guess what? It becomes nitrogen, the one next to it. The moment carbon number 6 loses a proton, it becomes boron number 5, okay? So it is the proton that defines what the element is, okay? And to lose protons is pretty difficult, okay? It's not an easy thing. For example, let me show you something. Here's lead right there, and here's gold, okay? You know, the alchemists that lived back, you know, they were the ones that were doing all this magic stuff. They were trying to make gold from lead. Well, think about this for a moment. In order for lead number 82 to become gold, they have to lose how many protons? 3 protons. Those protons are inside the nucleus. Not an easy thing to do. The moment you disrupt that nucleus, guess what? You have a pretty big explosion. Hence the atomic bomb, for example. So it's not an easy thing to do. All right. Let me get back to the slide here. All right, so number of protons defines the element. So carbon will always have 6 protons. I'm gonna lose electrons or gain electrons, lose neutrons or gain neutrons, but it will remain carbon as long as I don't lose any of the protons. Okay, so I talked about the atomic mass numbers because these masses are so small, so they're relative values. And so the mass, the AMU, the atomic mass unit for a proton and neutron is approximately 1, okay? And that for the electron, because it's so tiny, is 0, okay? So the mass number is equal to the number of protons and the number of neutrons. So how do we calculate the number of neutrons? Well, we go to the periodic table. You can take any element, okay, and we'll talk about this now. Underneath the symbol of the periodic table is a number. That's the atomic weight. Take a look at carbon, okay? Underneath the letter C, you see 12.01. That is the atomic weight for carbon, okay? Now, what we can do to get the mass number is we take that 12.01 and round it up to the nearest whole number. So rounding up 12.01 is 12, okay? Taking 12, which is a mass number, and subtracting 6, which is the atomic number, gives us 6. That is equal to the number of neutrons. Okay, let's do another example. Let's take boron number 5. Who can tell me, type it in or say it if you want, what is the mass number for boron? Anybody want to take a wild guess? Don't have to guess. It's nobody? Okay. Alexis, the 15.8? No. We want the mass number, which is a whole number. So we take the atomic weight, which is 10.81, round it up to the nearest whole number. What do you get? 10.081. No, not quite. Yeah. So 10.81, which is the atomic weight. Okay. 10 point, this is for boron. Can you all see that number 5 on the periodic table I'm sharing? Okay. Underneath the letter B is 10.81. That is the atomic weight. That's a decimal number. What we're trying to get is the atomic number, the mass number, I should say, which is a whole number. So we take that 10.81 and round it up so it becomes 11. Okay. Now subtract 11 from 5. So how many neutrons does boron have? It's 11 minus 5. Anybody want to type it in? 6, exactly. So boron has 5 protons, 5, I'm typing it in, electrons, and 6 neutrons. Okay? So boron has 5 protons, 5 electrons, and 6 neutrons. Okay, let's try, let's try sodium. Sodium's number 11. Okay, who can tell me how many protons sodium has? 11, exactly. Who can tell me how many electrons does sodium, the element sodium, have? 11, correct, Alexis? Now, how many neutrons does it have? Well, exactly. So by looking at the atomic numbers of any element, you know how many protons, how many electrons. By taking the atomic weight, rounding it up to the nearest whole number, that gives you the mass number, which is a whole number. Subtract the 11, it gives you 12. Okay, so there's 12 neutrons in sodium. Now, we're going to explain why these atomic weights are decimal numbers when we start talking about what we call isotopes. But let's get this part of this first. Okay, and so the neutrons is simply the mass number, which is a whole number, minus the number of protons. And we can get the mass number by rounding up to the nearest whole number, the atomic weight. Don't confuse the two. That's where we get the confusion. Atomic weight is the decimal number underneath the symbol. The mass number is a whole number. Okay. Sometimes we write the notation for, we write, in this case, let me explain here. You'll see it written as potassium 40, okay? So, and then they ask you the question, what is the atomic notation? Well, what we got to do is first find the symbol for potassium. All right, so the symbol for potassium is K, okay? the mass number is given to you, be -40. And so we can write it with the mass number with the 40 superscript left for 40. And then 19, we got to find from the periodic table what is the atomic number for potassium. Okay, so to do that, this is where you refer to the periodic table. We find potassium, which is K, number 19. Okay, and that's why this periodic table is so important. Later on, you're going to see this other information down here we're going to refer to quite a bit. We're going to be using this quite a bit. Okay, so going back, so that is the atomic notation for potassium 40, K, and then make sure superscript and the subscript on the left side of the symbol. Okay, not on the right side, but the left side. That's by convention, that is the atomic notation format. Now with this, how many neutrons do we have in potassium? How many, who can calculate that? Potassium 40 will have how many neutrons? Anybody want to try that? $20. That sound right? Because the number of protons and the number of protons, keep this in mind, the number of protons plus the number of neutrons must equal the mass number. There's 21. There you go. Okay. Notice the 21, and the 19 equal the mass number, because the atomic mass unit for the protons and neutrons is 1. So that number, always going to be whole numbers. Okay. All right, let's move on. All right, let's write the atomic notation for bromine. Well, we got to find the symbol for bromine. Okay, and so we use the periodic table. We'll go find it. Let me move my table. And bromine is a Br. Okay, it has how many protons does bromine have? You can tell me that. You can type it or say it. Either way. Bromine's right here, number. There's bromine. Okay, exactly. 35 protons, Alexis. How many electrons does bromine have? The element bromine. 35. That sound right? 35 electrons, that's correct. Anybody want, no, let me go back to the other problem. All right, because you'll notice here, we're talking about bromine 81, right? So that's the mass number, right? And so we can write bromine 81 on top, and 35 because that's the atomic number of bromine. And so how many neutrons would this have? 46. So bromine has 46. Now notice something. Here they're talking about bromine 81. All right. Well, if we go back to the periodic table, notice bromine, if we round that number up, 79.8, guess what? That is bromine 80. Okay. And the problem asks about bromine 81. So what do you think the difference would be between bromine 80 and bromine 81? Anybody want to take a guess? The difference is that bromine 80 has one less neutron, okay? Has 45 neutrons. Now you all heard about carbon dating, carbon 14, carbon 13, maybe carbon, you know, we got carbon 12, carbon 13, carbon 14. All those are carbon. The only difference between them is the number of neutrons. We got carbon 12 with 6 neutrons, carbon 13 with 7 neutrons, carbon 14 with 8 neutrons, okay? Those are what we call isotopes. It's the same element, but the difference between them is they have a different number of neutrons, okay? That's the only difference. They have very similar properties, but they're still carbon, but they only differ because of the number of neutrons, which brings me to the point. If you're ever asked the question, which is the most common isotope for fluorine, for example, all you have to do is take the atomic weight and round it up to the nearest whole number. In this case, ZZ is 19. So fluorine 19 is the most common isotope. If I take number 33, this is arsenic. I take the 74.92, round it up to 75. The most common isotope is arsenic 75, okay? The reason I can do that is because these isotopes are not in equal amounts in nature, okay? They are weighted depending on the percentage of how much of that isotope is in nature. Very similar to the class here. You have a percentage of your homework is worth a certain percentage, your quizzes are worth a certain percentage, the final exam is a certain percentage. Well, these isotopes are very similar. The ones that have a lot more of that out in the environment has a higher percentage, therefore their atomic weight is very close to the most common isotope that's out there. We'll do some examples here in a bit, okay? So we have carbon 12, carbon 13, carbon 14. All of them are carbon, okay? They all contain 6 protons. Remember, if you lose a proton, you become a different element because the proton defines that element. The neutrons and electrons do not define what that element is, okay? So carbon 12, they're giving you, they all have the same atomic number, which is 6. So we can determine how many neutrons each one has, okay? So carbon 12 has 6 neutrons because they have 6 protons, 6 electrons, okay? So carbon 13 will have 7 neutrons. Carbon 14 will have 8 neutrons. Okay? All of them are carbon. So let's take this example here. We got a table. First thing we notice, we have oxygen. All of them are oxygen, okay? So we go to the periodic table, we find the atomic number for oxygen, which is 8, okay? So we need that bit of information, all right? And also its atomic weight is 16.00. That tells me the most common isotope is oxygen 16, okay? So, but there are 3 isotopes, carbon 16, carbon 17, and carbon 18. They all have the same number of protons, 8, 8, and 8. Same number of neutrons, same number of electrons, 8, 8, and 8. Where they differ is the number of neutrons. Number of neutrons is 8, 9, and 10. The mass number is given to you by the hyphen number, hyphen 16, hyphen 17, hyphen 18. That is the mass number, okay? And the sum of the protons and the neutrons equals the mass number. So you might, oh, you know what? Bear with me. Okay, bear with me for 1 second, please. Okay, I'm back, sorry. Okay, so again, if you're given the isotopes, in this case, you're going to be given what the mass number is. Just it's written either oxygen hyphen and whatever number. That's the mass number. You identified that they're all oxygen, so they're all going to have the same number of protons, and they're all going to have the same number of electrons. Where they differ is the number of neutrons. Okay, so you simply subtract the mass number from the protons, and it gives you the number of neutrons. Okay, so as I mentioned earlier, the atomic mass and the periodic table, they're the weighted average of all the atoms for that element, all the isotopes. And so that's why they're not whole numbers. Okay, for example, we have carbon 11, carbon 12, carbon 13, carbon 14. Okay, the most abundant isotope is carbon 12, consists of roughly 98.89%. That's why when we look at the atomic weight, you know, and the atomic weight for the elements is the average of all the isotopes, the average of 11 and its quantity, the average of 12 and its quantity, 13 and its quantity, and etc. Okay, so that's why we have a decimal number for atomic weights, which brings me to the point. The atomic weights will never be used to determine significant figures. Okay, so don't use the atomic weights. And when you use atomic weights, use the atomic weights from the periodic table that we give you, because you'll find that different atomic weights, different periodic tables, there's different numbers there. So to be consistent and to make sure your answers are correct with the homework and quizzes, when you ever have to use the atomic weight, use it from the periodic table that we supply. Okay, so and that's why you can go to the periodic table and take the atomic weight and determine and round it up to nearest whole number and determine which is the most common isotope, because that atomic weight is the closest to the nearest isotope that's most common. I hope that makes sense. Okay, so you know, taking the average of whole numbers literally gives you an infinite number of sig figs. That's why we don't use sig figs from the atomic weights. All right. So the atomic mass reported for carbon is 12.01, which is close to the most common isotope of carbon 12, most abundant isotope. Okay, so we can look at the periodic table, and it says using the periodic table, determine the most abundant isotope for either lithium-6 or lithium-7. Well, to do that, we need the periodic table, okay? And we got to find it on the periodic table. Let me slide it over, and lithium is number 3. So we find lithium, take the atomic weight, 6.94. Voila, the most common isotope is lithium-7. Okay, we got that information from the periodic table. So lithium-7 is the most common isotope. Okay, now you're asked, which is the most common isotope, chlorine-35 or chlorine-37? Well, refer back to the periodic table. Okay, and find chlorine. Its symbol is Cl, number 17. Take the atomic weight of 35.45, round it up to the nearest whole number, which is 35, which then tells you that the most common isotope for chlorine is chlorine-35. Okay. A lot of the isotopes are radioactive and very unstable. Some don't last very long. So you'll find in the periodic table a mass number of, there be in parentheses because they're so unstable. Element number 96 is curium. That was named after Madame Curie, by the way. All right, chemical formulas. We're almost done with this chapter here. Chemical formulas tell us the type and the number of atoms present in the molecule. Okay, they don't really tell us the order that they're bonded together, but I can tell you, that in general, 90+% of the time, the first element that is presented to you normally is, for a compound, normally is the central atom, and everything else is bonded around it. Okay, we try to do that by convention, but that's not always the case. All right, now the number of atoms that we have in the compound, we use a subscript. So like H2O, 2 hydrogens. Now, those subscripts are etched in stone. You don't remove them. That's what they are. They come together in whole numbers. Okay. So H2O means 2 hydrogen atoms, 1 oxygen atom, for a total of 3 atoms. Okay. But again, they don't tell you anything about how things are bonded. We will, with time, when we get more and more into chemical bonding, you'll get the gist of how things come together, bonding wise. Okay, take a look at this compound, C3H6O3. All they're telling you is that there's 3 carbons, 6 hydrogens, and 3 oxygens. Okay, so we have a total of 6 atoms involved there. 6 atoms. So this is important to learn to count all the atoms. Why? Because every atom there has an atomic weight. So we have 3 carbons which have atomic weight of 12.01 for each one. So to get the atomic weight for this molecule they present you, we take 12.01 multiplied by 3. Every hydrogen is 1.01, multiply that by 6. Every oxygen is 16, multiply that by 3, add that number up, and that is the atomic weight of that particular compound. Okay, we're going to use that quite a bit down the road. So identify how many atoms in a molecule. Now, if we ever need to say, like I said, the subscripts, we don't do anything to the subscripts. But if we ever need to show that we need more than one of those, we put a 2 in front. So for this example, let's say H2O, I can't make subscripts, so this is H2O, okay? HCO. That's the coefficient there, the subscript. I can't change that. But if I want to show I got 2 molecules of water, I put a whole number in front of the whole thing, like 2. I can change that number as many times as I want. I can put 1,000 there if I want. Okay, that is the coefficient for that molecule of water, but I cannot change the subscript. All right. So take a look at this species here. Something interesting here. You see a parentheses, okay? And then you see NH4, and then N parentheses, subscript 2, okay? The fact that you got a parentheses, this is a unit. They stay together. We're going to be dealing a lot with those. So NH3 is a unit that we keep together. And to designate that we need more than one, we put parentheses around it, and then we add a subscript. In this case, we need 2 of them, okay? 2 of them. And then we got a carbon and then CO3. So keep this in mind. Since the parentheses is there, that means I have 2 nitrogens and a total of 8 hydrogens coming from the NH4 unit, okay? And I have 1 carbon and 3 oxygens. So I'll have a total of 14 atoms total for this species right here, this compound. All right. Here, they're asking you how many atoms in each formula. Well, of course, right now we don't know what they are. That's okay. We want to identify how many atoms in this particular material. But I'm going to tell you what that is. H3PO4, if you drink a lot of soda pop like I do, you probably drink a lot of that. It's called phosphoric acid. Okay. So that has 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay. Whoa. So there are a total of 8 atoms in that molecule. The next one here, this has a name. This is called calcium hydroxide. We're going to learn these names here with time. Okay. If you eat Tums, this is what you're eating. You'll find a lot of calcium hydroxide in Tums if you have furan acid. Okay. That has 1 carbon. Here, look at this. We got a parentheses, OH. That's a unit there. In fact, that unit has a specific name called hydroxide, but there's 2 of them. That means I got 2 oxygens and 2 hydrogens. So for calcium hydroxide, I have a total of 5 atoms. The next one, it has a name called aluminum sulfate, used for a number of things. But notice there's a subscript in front, under, after the aluminum, Al. Okay, there's 2 aluminums. Again, we got a parentheses. This is a whole unit in itself, SO4. It has its own name called sulfate. But there's 3 of them. 3 of those units in parentheses. So we got 3 sulfurs and 12 oxygens. So we have a total of 17 atoms in that compound. $17 atoms. Now that later on, once we figure out how many aluminums we have, for example, how many sulfurs, how many oxygens, each one of these atoms have an atomic weight. So we can figure out the total, the atomic weight, well, we'll call it molecular weight for this molecule of aluminum sulfate and calcium hydroxide and H3PO4. Okay. So, but first we have to learn to identify how many of each atom there are in the molecule. Now, the law of definite composition or definite proportion tells us that when compounds come together, they have a specific percentage. So H2O, whether we have water here in Arizona or we find water in China or wherever, and when we analyze it, it will always contain 11.2% hydrogens and 88.8% oxygen, okay? And that's because the way how many hydrogens and how many oxygens came together to form water. So that is the law of definite composition. We use that quite a bit. And, you know, you're out in the lab making a compound, we always send a sample off for analysis to determine how much carbon, how much hydrogen, how much sulfur, nitrogen, what percentage. We can use that information to back calculate to figure out the actual formula for the compound to help formulate it. Okay, now with that being said, guess what, guys? We're done with chapter 4. All right. So, and just in time too, I got 2:59. So don't forget about the quiz today. Okay, so give yourself plenty of time to finish it. If you have any questions, feel free to send me an email. I'll try to get back to you as soon as I can. So anybody have any questions in general? Okay. Well, thank you for showing up. We got 4 out of 29. Okay. That's all right. All right. Well, thank you, Alexis. All right. You guys stay safe out there. Okay. Sonia, how are you doing? You can unmute if you want.
So sorry, give me 1 second here.
Yeah.
Right now, there's nothing really other than,
Okay, sorry about that. I'm
Nope.
at work.
I heard the background, everything.
Yeah. So I was kind of going, I mean, we already went, I emailed you, but I was kind of like looking over through like some of the problems that I did do.